Hello and welcome to Tech Simplified TV. This is the fourth episode in VLSI Milestone series. In today's episode, we will talk about strained silicon. Do you know, introduction of strain in conventional silicon can boost mobility along the channel? Yes, that's an amazing fact, and industry rightly utilize this property of silicon. In today's episode, we will try to understand how this mobility boosting happens. If you are interested, stay tuned till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, VLSI milestone and strained silicon. Second, what is strained silicon? Third, what is silicon germanium? When we are discussing about strained silicon, it's very important to understand silicon germanium, as silicon germanium is used as strain creating material. Introduction of strain in conventional silicon is done by multiple mechanisms. One among them is use of silicon germanium. So we must understand silicon germanium and its basics. How strain is created in silicon, impact of biaxial tensile strain, and finally impact of compressive strain. So we are done with this slide. Now let's move to the first slide. VLSI milestone and strained silicon. This is the diagram we are taking reference for last 3 episodes. Here also we will take reference from here. Strained silicon is mentioned here with timeline 2004 and 2008 with technology node 65 nanometer and 45 nanometer. Now, we have already discussed SY substrate which were introduced at 90 nanometer 2003. After 90 nanometer, this strained silicon has been introduced. From 90 nanometer technologies, the performance boost by method of MOSFET dimension scaling started to diminish. Till now, MOSFET dimension scaling was the success route to get better device performance or MOSFET performance or circuit performance. Now from 90 nanometer, the benefit started to diminish. Different substrate, then strained silicon, here high K metal gate. These all started to get introduced. These are alternative ways, and also they are technology boosters, because when the existing technology or method stopped to give benefit, at that time these new technologies introduced in the system to boost the performance. Now higher body doping leads to lower carrier mobility, higher junction capacitance, increased junction leakage. Keeping the gate voltage same, if we use body doping, that is the substrate body, that if we increase the doping to get more carriers, free carriers at the same voltage, then that do not increase the mobility, rather it decrease the mobility, and that creates high junction capacitance and junction leakage. So more junction capacitance means more delay in switching, and increased junction leakage means whatever benefit we were trying to get is all gone through this leakage. Inner gate dielectric leads to higher leakage current. Inner gate dielectric and higher gate leakage, that is a scaling related issue. As we move to lower nodes, gate dielectric becoming more and more thin, the gate leakage current becoming very predominant. And at 32 nanometer, we replace the conventional dielectric material, that is silicon dioxide, with high K material. We have already discussed that part, this higher gate leakage current and high K, in our high K episode. So strained silicon channel has been introduced as technology booster. We said that strained silicon basically boosts the mobility of the carriers. The mobility enhancement obtained by applying appropriate strain provides higher carrier velocity in MOS channels and drive current at the same supply voltage and gate oxide thickness. Strained material is used as a channel because the conduction is at channel. We need boosted carrier mobility at channel, not at the body. So strained layer is used as a channel material. We get mobility enhancement. Now, tensile and compressive strain applied to channel. Tensile and compressive strain, there are 2 types of strain, tensile strain and compressive strain. Now, strain changes lattice constant and energy band structure of silicon. In later slides, we will understand how lattice constant is changed and energy band structure is changed. And gradually, we will understand how this change in lattice constant and energy band structure result in higher mobility. So, we are done with this slide. Now, let's move to the next slide. What is strained silicon? Strained silicon is literally silicon which is strained. Yes, conventional silicon, when it's strained, that is called strained silicon. we need to introduce strain in conventional silicon so that its band structure and lattice constant changes and gives the boosted mobility. So strain is induced using different mechanism. In strain, silicon atoms are stretched beyond their normal interatomic distance. And advantages of strain silicon relies in its ability to fundamentally alter the band structure in ways that increase the effective mobility. Any material has its normal interatomic distance, that is lattice constant, that is actually stretched beyond its normal interatomic distance by different mechanism. The whole structure is either compressed or stretched so that it doesn't remain in its original position or don't follow the original structure. So it's always in either tensile strain or compressive strain. Advantages of strain silicon relies in ability to fundamentally alter the band structure. This strain basically altered the band structure and thus we get a benefit of mobility increase. The basic idea in strain silicon CMOS is to modify the carrier transport properties of silicon by introducing strain in order to improve performance of MOSFET. So strain is applied, band structure is changed and carrier transport property is improved. So we get better or improved performance of MOSFET and as well as the circuit. Mobility improvement in strain silicon takes place mainly due to the reduction of carrier conductivity effective mass and the reduction in the intervally phonon scattering rates. The applied strain actually changes the band structure. When band structure is changed, conductivity effective mass of the carriers that got changed and subbands where those electrons stay, that basically their positions changed. Since the positions changed, phonon scattering rate changes. So mobility get boosted. Semiconductor with smaller lattice constant than substrate leads to tensile strain on top layer and semiconductor with larger lattice constant than substrate leads to compressive strain on top layer. We will understand this from this diagram. There is a component with a certain lattice constant and here is another component with certain lattice constant. That is, interatomic space in this material is different from this one. And from the diagram we can easily understand that interatomic space is much larger in case of this material. Now when we have a substrate of this material and we are trying to grow this material on that substrate, what is happening? It's just to accommodate this material is getting stretched. From this diagram also we can understand it's getting stretched. And here if we use this first material with smaller lattice constant as a substrate and try to grow this second material with larger lattice constant on it, so this second material will get compressed. Just to accommodate within this structure or just to follow the same structure, it's getting compressed. So semiconductor with smaller lattice constant than substrate leads to tensile strain on top layer. This one. Smaller lattice constant than substrate leads to, this is the tensile strain, and with larger lattice constant than substrate leads to compressive strain. This is larger lattice constant and substrate has lesser lattice constant, so it will be compressed. That is compressive strain. Now we are done with this slide. Let's move to the next slide. So what is silicon germanium? So this is basically cubic silicon with lattice constant 5.431 angstrom, and this is cubic germanium with lattice constant 5.6466 angstrom, and the altogether mismatch in lattice constant is 4.1%. So basically this is silicon and 4.2 here it's germanium if we represent it in that way, right? And silicon germanium has a lattice constant in between these two depending on the percentage of germanium, that is X. If germanium is 20%, then rest of the 80% is silicon. So silicon germanium is an alloy with molar ratio of silicon and germanium, that is with a molecular formula of the form silicon 1 minus X germanium X, used as semiconductor material in integrated circuits as strain inducing layer for CMOS transistor. Now since silicon and germanium, they have lattice constant difference, when we develop this silicon germanium alloy, they have a lattice constant in between 5.431 and 5.646, and that is also greater than silicon, obviously, because in this line silicon is at the minimum and germanium is at the maximum. If we grow silicon on silicon germanium layer, or this is the silicon germanium is substrate and silicon is epitaxially grown on that silicon germanium. Obviously on top there will be material that is silicon with lesser lattice constant, and below it will be with a material that is silicon germanium with greater lattice constant. In this process we will have a biaxially strained silicon, and these are the direction of strain, that is basically this direction. The whole layer of silicon is globally strained, not a particular direction. In two direction it's strained because it's getting stretched in these two direction, this direction and this direction, right? This is biaxially strained silicon. It's a standard method, and that's why we have added this slide. The biaxial tensile strain in the strained silicon on relaxed silicon germanium can be tailored by germanium content, because strain is caused by the lattice constant of silicon germanium. Now lattice constant of silicon germanium can be altered by this percentage of germanium. Germanium percentage alters the lattice constant of silicon germanium, and that mismatch actually creates strain in silicon. So how much strain should be applied on silicon? We can control it by controlling the percentage of germanium. Now silicon germanium is used for fabrication of silicon germanium heterojunction bipolar transistors and strained silicon MOSFET, advanced CMOS and BiCMOS technologies. Silicon germanium has its use in many places like silicon germanium heterojunction bipolar transistor, strained silicon MOSFET as we can see, and BiCMOS technologies. So we are done with this slide. Now let's move to the next slide. Strain is created in silicon. Two types of strain, tensile and compressive. We have seen two types of strain are there, that is tensile and compressive. Two direction of strain, that is biaxial and uniaxial. Tensile strain is basically biaxial on relaxed silicon germanium, and this strained silicon here it's two direction, right? Along these two direction. Now if silicon germanium, which has obviously a bigger lattice constant compared to silicon, if silicon germanium is developed on silicon, that get compressive strain, that compressively strain, and that is also biaxial compressive strain, because for whole area the silicon germanium layer is getting compressed because of silicon substrate. Here in this diagram we can see silicon germanium graded buffer. This buffer layer is created by gradual, and from here to here in the whole thickness of this buffer layer the germanium percentage is not constant, it gradually changes. Why it's called global? Because of the strain is along the whole layer, introduced by epitaxial growth of silicon and silicon germanium layers. Biaxial strain may be tensile or compressive. Example of tensile strained silicon on silicon germanium, and compressive strain is just opposite. Silicon germanium on relaxed silicon substrate, the strain is induced by the lattice mismatch between silicon and silicon germanium. Now what are the advantages of this process? Uniformly strained layers obtained. So whole layer is uniformly strained, can be implemented with standard CMOS process. That's a great economical advantage. When a new process can be incorporated in the standard existing process with some modifications, we always try to follow that because of expense. Now disadvantages are also there. What are those? Limited improvement of PMOS transistor performance. Actually this process basically improves mobility or performance in NMOS devices. In PMOS it's not very significant. Occurrence of defect and dislocations at boundary surfaces increase production cost. Introduction of new material altogether, silicon germanium, that increases cost. Uniaxial or local strain, that is introduction of local structures and materials cause strain in the channel of transistor. This is local or uniaxial. Strain could be introduced in some other way, that is local structure, using local structure and material. Silicon germanium has greater lattice constant, so we make source and drain with that. So this source and drain will create strain in this channel. In PMOS, the source and drain are formed by epitaxial silicon germanium, which introduces uniaxial compression in the channel area. A tensile capping layer in NMOS creates uniaxial strain. These are uniaxial, one directional, not in two direction. In one direction, this strain is created. So, local materials like here, locally we are making not the whole global substrate or above there is a buffer layer. No, we are just creating this source or drain, and in PMOS, we do it in NMOS, there is a tensile capping layer that creates uniaxial straining channel. So we are done with this slide. Now let's move to the next slide. Band structure of silicon. Now, band structure of silicon, we have already discussed. Strain actually changes the band structure. So we will understand the basic band structure, then we will try to understand how strain modify this band structure and leads to higher mobility. Now, each energy level of silicon is composed of 6 equal energy values in 3 dimensions. This is 6-fold degenerate values. Degenerate values mean all of them have same, their directions are different. 001 direction, it's a crystal. Crystal have direction, and these perpendicular valleys and these in-plane valleys, all of them have same energy level. 6-fold degeneracy. Degenerate means multiple valleys. Energetically, they are at same level, although their directions are different. In inversion layers, these 6 valleys are split into 2-fold out-of-plane valleys located at KZ axis, that is 001 direction, and 4-fold in-plane valleys in KX direction and KY axis, that is 010 and 100 direction. The electrons in all these conduction valleys have transverse mass, which has value 0.19 m0. m0 is free electron mass, and longitudinal mass, which has value 0.916 m0. Now, clearly from this value, we can understand that longitudinal mass is greater than transverse mass. So, transverse mass is less. Remember this point, transverse mass is less. Now, in these 2-fold valleys, electrons have transverse mass parallel to the MOSFET silicon dioxide interface and longitudinal mass perpendicular to interface. So if we draw a cross-sectional view of source, drain, oxide, and this is basically metal, that's electrode. This is oxide. This area is basically oxide. Now, what we are saying, the electrons have transverse mass parallel to the MOSFET silicon dioxide interface and longitudinal mass perpendicular the interface. That is the interface. Perpendicular means this direction, that is longitudinal mass ML, and in this direction parallel to interface is MP. This is the situation of this 001 direction, that is 2-fold values. On the other hand, in 4-fold values, the electrons have transverse mass perpendicular to the MOSFET silicon dioxide interface and longitudinal mass parallel to the interface. And this in-plane valley, their longitudinal mass is parallel to interface, this direction, and empty is this direction, just opposite to the 2-fold values. These are the unstrained silicon condition we are saying. Now there are 3 valence subband, that is heavy hole, light hole, and split off. We can see this heavy hole and light hole, they are degenerate. There is a degeneracy here and they are joined here energetically, and this split off hole is quite far away. This is the situation in basic silicon. Now we are done with this slide. We will move to next slide. Impact of biaxial tensile strain. This is the unstrained silicon. Here we can see these 2 valleys are bigger in size. That means they are energetically splitted and coming downwards. This is the convention of drawing these valleys, and these are smaller. That here it's 6-fold degenerate. That means all 6 valleys, their direction might be different, but they are at same energy level. Strain splits them. These 2 vertical 001 direction valleys energetically move downward, and these 4 in-plane valleys energetically they move upwards, and we always know that electrons prefer to stay in lower energetical value. With tensile strain, 2 out-of-plane delta 2 valley move lower and delta 4 valleys move upward energetically. These band alteration gives an alternate lower site for electrons to reside, that is delta 2 valleys. Now value of MT in the lower energy valleys, delta 2 is lesser than the delta 4 valleys in direction parallel to the interface suitable for the flow of electrons from the source to drain. Inter-valley phonon scattering between the lower and upper state is decreased. Due to this, the electron mobility increases. Energetically, they move downwards. All these delta 4 valleys and delta 2 valleys, they move separate. They get separated energetically. So, scattering also decrease. Due to these 2 things, electron mobility get increased. With strain, valence subband also splits. Here, heavy hole, this subband move this way, and light hole moves upwards this way. So, both in-plane and out-plane hole mobility is improved mainly due to reduced interband and intraband scattering. So we are done with this slide. We will move to the next slide. impact of compressive strain. This is the unstrained silicon, and in compressive strain, these two move upward. That is, out of plane delta 2 valleys, they move upward, and these 4 in plane valleys, they move downward. And heavy hole valence band, here the uniaxial strain has much more significant advantageous effect on the valence band relative to biaxial stress. So we are done with this slide. So we are done with this discussion. Now let's conclude our today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. If you have a question or query, put it as a comment. If you have a dislike, also mention it in comment section. Thank you again and bye for today.